No, no sé.
Y luego arriba el plan,
Okay, so welcome everybody to the second session of the day. So our speaker is Emilio Martínez-Núñez. He's coming from the Universidad de Santiago de Compostela. He finished his chemistry studies in 1994 and he obtained his PhD in 1999. He was appointed as a Ramón y Cajal researcher from 2001 to 2006. And since 2007, he is a professor titular at the University of Santiago de Compostela. He has been visiting professor in several universities, among them the University of Leeds in 2013 and the Université de Lille in 2018. And his current research interests are around the design of automatic methods to discover reaction mechanisms and also energy transfer models in gas surface collisions. So he's the main developer of AutoMechin, which stands for Automated Discovery of Reaction Mechanisms and Kinetics. And besides being an excellent lecturer, as we will see in a second, he also has also a very interesting research background with more than 3,000 citations and an H index of 27. So please, Emilio, for yours.
Thank you very much. I hope you can hear me well because I caught a cold a week ago and my voice is not in perfect conditions, not 100%. Anyway, so what I'm going to try to explain today is how to find reaction mechanisms in an automated manner. So what we are doing here, or what typically people have been doing over the years, is to study reaction mechanisms, is to try to find all the steps, from reactants to products through different intermediates using chemical intuition and doing all these searches by hand. And the method we are going to propose, I'm going to show you today in this lecture and in the afternoon in a computer session, is something to do everything, to do the workflow in a fully automated fashion. So, we use MD simulations, but they are reactive MD simulations because we want to study the breakage and formation of chemical bonds. So we want to study reactions. So what kind of reactions? So first of all, because people typically ask me, what kind of reactions do you study with this method? So we've been studying things like reactions interested in combustion chemistry, astrochemistry, homogeneous catalysis, for instance. We haven't studied gas surface so far, but it would be possible to study gas surface reactions as well. And these are the kind of systems we typically study. So I have to say, first of all, that if you have any questions, please interrupt me anytime, because I prefer something more interactive, because I think I have 2 hours and this is too much. And we can have a break, of course, of 5 minutes, but you can interrupt me anytime. I really prefer interaction, discussion. So we've been working on this project for about 7 years now in our group in Santiago de Compostela. And as Ines said in the presentation, we developed a program by the name AutoMaking. AutoMaking stands for Automated Mechanisms and Kinetics. So we predict automatically everything, the reaction mechanisms, and then the kinetics as well. So basically, we try to do, we developed a workflow to do a computational experiment in which you can predict branching ratios for the different products in a completely automated fashion. It is, as I said, basically based on MD simulations, but we have also some other algorithms that are probably more suitable for, things like homogeneous catalysis or big systems. We should probably try to use other type of algorithms, as I said. But today, the method is probably 80% MD simulations, 20% other algorithms. So this is the outline of the talk. So basically, the first part of the talk is going to be about the method itself. I will tell you all the details of the method, most of the details of the method. Again, if you have questions here or there or after the method, please ask me. And then in the second part, I will tell you about some of the applications we have been studying in the last 7 years. So the question here is, why should we care about using automated procedures? So, well, one of the reasons is because the typical way, as I said before, in which people face this kind of problems is to try to do, to find all these things by hand, all these, pathways, all the intermediates and the transition states using chemical intuition. And this is very demanding, But the most important reason is because many times you miss some mechanisms. You might miss mechanisms. And this is just an example, simple example of a small system. This is just a 7-atom system, a vinyl cyanide molecule. I don't know if you can see from the back of the room. But anyway, this is a 7-atom system. And still, the mechanism shown here in green was found only thanks to AutoMaking. The other ones we found with, using the traditional approach, but this other one, which is nothing really very complicated, but, the thing was that what we did to study the system by hand was to compare with similar systems, and the 3-center, 4-center, and 5-center mechanisms were reported before. So we started with these structures, which is a typical procedure, and this one here was overlooked. This mechanism here that goes, and look at the transition state, it's not very high in energy. So this is the most important reason for using automated procedures. So chemical intuition is fine, but sometimes, you need something else. So this is the workflow, general workflow of the method. Well, basically, you start with a structure for the system, any kind of a structure. Doesn't need to be optimized. You can get it from wherever you want. And then the method has different methods. Sorry, the program has different methods implemented. As I said, MD simulations. You can also use heuristics methods based on chemical knowledge. We also employ graph theory. And then for the kinetics, we use kinetic Monte Carlo to solve the chemical master equation. So this is what comes out of the method. So you can generate automatically the energy profiles for the different mechanisms and different pathways. You can get the structures fully optimized. And you can plot something like this with the kinetics. This is the population of the species as a function of time. You can see the decay of the reactant, the buildup of the different products. You can see some population for some of the intermediates. And this is very, I guess this is very useful. And obviously, the infinite time population for the products gives you the branching ratio for the different products. So this is the type of results that we get. And these are the methods that I will explain in detail in a moment. So this is again the pipeline. So we have an input geometry. We optimize it, and then we can choose between MD simulations or an algorithm that is based on chemical knowledge, heuristics. After that, we need something to detect the reactive events, because what we do is we propagate trajectories, a number of trajectories, very short trajectories, and then we need to analyze the trajectories because we try to find structures that resemble transition states. I mean, there are other methods that employ MD simulations, and they are based on optimizing minima from the MD simulations. And once they have the minima, they connect the minima through optimizing the reaction path and then getting the transition state using different methods. But here, we proceed the other way around. It is more difficult, but I think it is advantageous in different ways. So we try to find directly the transition states. And then from the transition states, you get the minima. There is two reasons, at least, to explain why this is more advantageous. So the first one is because there can be more than one transition state connecting the same pair of reactant products. This is one thing. And then the second thing is, doesn't really matter whether you start from one molecule, so you study unimolecular reactions, but you can get transition states for bimolecular reactions as well. I mean, and the reason for that is because the MD simulations, most of the MD simulations are high energy simulations. And that means that they do not follow the minimum energy path, or the IRC. They are just, flying up in the sky, and they can jump from one IRC to the other. So you can start from one molecule only and follow closely a given IRC, and then you can jump to another one, for instance, to a bimolecular reaction. So this is one, I guess this is an advantage of this procedure. So once you detect this guess TS structures, guess transition state structures, you obviously want to optimize the structures because this is just a guess structure. You optimize it using the typical eigenvector folding algorithm, for instance. And then once you fully optimize the structure, you have to do some screening because you run MD simulations in parallel and you obtain repetitions of the structures. So you want to compare the structures, so you need to screen the structures. And after that, you create a database with all the structures. But then obviously you need to connect the transition state to the reactant and the product. And for that, you run minimum energy path calculations or IRC calculations to get the reactant and product connected by the given transition state. After that, you have another database with the minima. And once you have the minima and the transition states connecting them, you can build the reaction network with all the connections between the different minima through the different transition states. That's the so-called reaction network or chemical reaction network. And finally, you can solve the kinetics and the conditions of your interest on the created reaction network. This is the last step. So this, as you can see here, there are several tasks in blue which are carried out at what I call here low level. LL is for low level. And so by low level, I mean semi-empirical calculations like XTD or the type of calculations you can run with MOPAC, for instance, PM6, PM7. The reason is because they are cheap and fast. So you want to sample everything in a fast way. So we use, as I said, semi-empirical calculations for that. But obviously, then you need to re-optimize everything. You want to re-optimize the structures. And then also, a given structure, once you have the structure, you also need to rerun the minimum energy path, because at different levels of theory, there is no 100% match between the MEPs at both low level and high level. So you need to re-optimize also, or sorry, to rerun the minimum energy path as well, because a given TS can connect different structures depending on the level of theory. So you need to recompute everything again at low level, high level. Sorry. By high level, by the way, can be any type of level, BFT, any initial calculation of your choice, depending on the size of the system and the size of the network. You can choose one method or the other. So you recompute everything, and you have now a database with the minimum TS at high level, and also a reaction network at high level, which again does not necessarily need to be exactly the same as the low level one. That's why you obviously need to rerun the kinetics again on the high level reaction network, okay? At the conditions of the universe. It could be a given temperature, a given energy, so fixed temperature, fixed energy, whatever. This is basically the workflow in more detail of the program. And now I'm going to go through the different steps to explain you in more detail. So we have two types of MD simulations. What we call here standard MD is just what we do here is just we put a lot of energy into the system or temperature into the system, because we want the molecule to break apart in just a few femtoseconds. And with few, I mean something like between 100 and 500 femtoseconds, something really fast. So we put a lot of energy into the system, and the problem with that type of method is that there is a well-known bias towards high entropy transition states of the MD simulations. So they tend, in phase space language, phase space is the space of Q's and P's converting at some momenta of the system. That is like a bottleneck when you go from reactants and products. And the wider the bottleneck, the easier for the system to go from reactants to products. And this is connected to entropy. So there are different combinations for the system to go through the transition state. This is what I mean by high entropy. Or in terms of the frequencies, it means, or the density of states, it means there is a higher density of vibrational states for high entropy transition states. So, and those states are going to be biased by MD simulations in general. And this is even more problematic when you go up in energy. This is a problem. Yes, it is, because you are going to get more of those transition states compared to those that are less entropically favorable. Okay, so this is one thing we have to play around with. And so something that we do to minimize the problem is to use, instead of one fixed energy for the dynamics, we use a range of different energies. Because again, as I said, this is more problematic for high energies. So for high energies, transition states with high entropies are even more favorable than the other ones. So we select a range of energies, and we go from low energies to high energies. Try to sample everything, enthalpically and entropically favored transition states with more or less the same probability. Okay, this is one thing that we do to minimize the problem. And so this is an example of a typical movie that you can see using the program, and look at the energies. This is 210 kcals per mole, so huge energies. Okay, because you see here, you break things in a very short period of time. This stage, I don't remember, but this could be less than 110 seconds. So you break things quite fast.
Do you allow the exchange between structures of different? You are running different reactors at different energies.
Yeah.
You have a sampling of different energies, but do you allow the exchange of structures between these different energies in order to, for example, if you are running at very high energies, you have these more broken systems. Mm-hmm. Maybe if there are some quantum Monte Carlo regular dynamics programs that allow this exchange in order to fast relax the system or maybe make it very fast as well.
I know what you mean. I know what you mean, but no, we don't do anything like that here. So basically, what we do is we do both things: low energies, high energies, and then we analyze everything, and then we merge everything together after.
Okay.
But we don't do that. No. It could be possible. But we don't do that here. So we use an energy range, which is again is also it is an adaptive energy range. By adaptive, I mean that depending on the reactivity, you put the boundary in a different position because you want some reactivity. Obviously, if you run 100 trajectories and you don't find anything, you change the boundaries, obviously. And this is done automatically also. But the second way, there is a second way to remedy the problem. This entropic bias problem, which is to use rare event acceleration methods. And this is similar. This is in a way related to your question, Danilo, I guess. It's not exactly the same. But, so what we use here is something called DXDE. DXDE well, it stands for box space dynamics in energy space, and the idea is simple. So what we do is we split the system in different boxes of energy or windows of energy, from low energy to high energy, and then we start from the lower energy box, from the lowest energy box, and we do the dynamics there. We confine the system there, and we follow the dynamics there, and we sample what happens there. We sample all transition states there, and once we are happy with the results, we allow the system into the next box, and so forth. So that way, we are going to sample both entropically and enthalpically transition states more or less with the same probability, because we are doing things in a better way. So this is more efficient from an algorithmically speaking. So you get more transition states for the same simulation time compared to standard ND. Although we have a problem, there is a latency issue because the way the semi-empirical program is called here is this is done via a library called Atomistic Simulation Environment, and therefore there is a latency issue because this has to call MOPAC or any other program whenever it needs the gradients to integrate the trajectory. So there is this problem from a computational point of view, but the algorithm itself is more efficient. So this is something that we obviously know how to solve it, but it hasn't been solved so far. So this is again another example of one trajectory run with DXDE. You see that things here go more slowly, and then you can see some oscillations sometimes. And this is when the system is colliding with the boundaries in a given window. Okay, and we use Langevin dynamics here. So this is another difference. Okay, so this is also implemented in the method. So far, typically, if people ask me which method to use, I would say the other one because of this latency issue. Okay? But we are working on this. We are trying to make it more efficient from a computational point of view. Okay, so again, as I said at the beginning, this is fine so long as you're studying small systems. I mean, if you study something like, I don't know, combustion chemistry, systems up to, I don't know, 10, 20 atoms, this is fine. You can use MD simulations, no problem. And the programming is very efficient. But as you go, as the system grows bigger and bigger, there is obviously a combinatorial explosion, pathways, structures, and everything. So you don't want to use MD simulations there because you can easily get thousands and tens of thousands of structures. And it is very difficult to manage that. So one alternative could be to use chemical knowledge. And we have a module which is called ChemKnow for chemical knowledge. What we do here is to use, we employ graph theory. So I don't know if you're familiar with graph theory. So how many of you are familiar with graph theory? 2 people, 3, 4 people, 5. Well, anyway, so in graph theory, a graph is made up. I mean, you can think of a graph as a molecule, for instance, because a graph is something like this molecule, water molecule, for instance. A graph is made of nodes and edges, something like that, in a similar way as a molecule is made by atoms and bonds. So a graph would be a molecule where a node is an atom and an edge is a bond. This would be a graph. And then one way to represent mathematically the graphs is by using a matrix like this one here, which is called adjacency or connectivity matrix, because essentially gives us the connectivity of the atoms, as you can see here. So it's made up of zeros and ones. You have a one whenever there is a bond between a pair of elements. For instance, there is okay, this is a square symmetric matrix, first of all. And you can see that there is a one there because there is a bond between atoms 1 and 2. There is also another one here between 2 and 3. And so this is a convenient way to represent a graph or a molecule, if you like. And so the interesting thing of this procedure is that you don't do the reactions in geometry space. What we do is we transform the geometry into something like this, a graph like this. And then you do transformations of the graph. So we do graph transformations. We change ones by zeros and vice versa. When we change a one by a zero and vice versa, what we are doing is we are breaking and we are forming bonds, right? Okay. So this is what we do. And we have to do that according to some rules. And the rules we use are these things here. So first, oftentimes when the system is big, homogeneous catalysis, for instance, you have the catalyst, but not all the atoms of the catalyst are going to be active. So not all the atoms in the catalyst are going to intervene in the reaction. So you can select a number of atoms, active atoms in the system, which typically is much fewer than the total number of atoms of the system, sometimes. So you have active atoms, then you can define the maximum bonds that can break at each step. So maybe you can say only 2 bonds can break and form. And this is very typical. It is very rare to find a transition state with more than 2 bonds being breaking or formed. I mean, you can say 2, 3, whatever you want, depending on your system. This the user has to decide. And we can also select the minimum and maximum valence of the atoms. You don't want a carbon with 5 bonds, for instance, right? So this is something that you set at the beginning, and then you do all these transformations according to these rules here. So this is what we do. So as I said, first we transform the geometry into a graph, into an object like this, and then we do the graph transformations according to these rules, and then we find new paths. And after finding a new path means we find a new minimum in the system. Okay, and here we proceed as many other programs. I mean, we have 2 minima, and then we obviously need to connect it to minima. And then for that, we use NEV, next elastic path. I know there are other methods to connect, to optimize the reaction path, but this is a very convenient method. And so this is what we do. So basically, we optimize the path between both the reactant and the product. And then from the highest point along the path, we take the highest point, and we use that as the transition state guess structure. And then we optimize it. Okay? This is what we do. So the procedure is different from the other one, but the remaining steps are exactly the same as I said before. So once you have that, you create a database with the minima, with the transition states, you create a reaction network, and then you run the kinetics. Exactly the same. So we just change the way in which we find the structure, the transition states and the products. And there are several algorithms for these transformations, by the way. I mean, from geometry to graph is simple, it's very simple. From graph to geometry is not so simple, it's not straightforward, but we have several ways, several algorithms to do that. Okay. Okay, this is the workflow for this one here. This is very new. We implemented this, I guess, like 1 year ago, and we're still, working on that. Yes. Okay. Anyway, either using empty simulation. Yeah. What?
Just one question from your previous slides, the molten one. Even one more. Yeah. So you have told that you are taking ranges of energies from lower to higher depending on the molecules. So while running the simulations, how we are deciding that at which, like every 100 step we need to take the, like you said, you are taking the box So
But the box is in the other
so
method.
because in like while running the simulations, we will be having interactions also between the molecules.
There is only one molecule here.
Okay, so
Only one molecule. Yeah. There could be more than one molecule.
in complex systems, that problem.
There could be more than one molecule, but in systems with more than one component, more than one molecule, I wouldn't do MD simulations. I would go for chemical knowledge rather than that. Yeah. So far we've been using MD simulations to study only one molecule. Yeah, so far. So, but I don't know the question. Maybe I can answer the question anyway.
So,
I don't know. Go to the question.
my question was like in where there is more molecules, so there will be intermolecular interaction. So because of that, the energy might increase. So
Yeah,
I mean,
in a given molecule. You mean?
Yeah, the overall.
Yeah.
So,
No, the overall is constant.
No, sorry, the in between, because every 100 step if you are taking, then it will matter. So in that case, we will go for the low energy, low interactive one or higher interactive, like where there is lower interaction between the molecules, because energy will be less, not the overall, but in between energy. So I think, in that case, we can look for the lower interactive cases.
I'm not sure if I understood your question well.
So basically, my question was for like complex systems.
Yeah. Yeah, I mean, obviously there is energy transfer, and the energy of the molecules change in these collisions, and but still there could be reactivity in a single molecule or between molecules. By the way, we have also a method to study intermolecular interactions. Maybe at that point you can ask me the question again and see if.
The question about the network method. Which limitation have you found in kind of atoms, like transition metals? Have you found any limitation on scalability?
You mean constructing the reaction network?
Yeah. And also,
in terms of scalability, is more the problem with the previous steps, not the reaction network itself. To be honest, I have tried only in systems that create networks with something like 1,000 nodes, which is, well, it is okay, but not too much. It's not 1 million. But so I haven't found any problems finding, creating the reaction network itself. When you go to big systems, problems arise before that. I mean, trying to get all the transition states, etc. Because in that case, there could be millions. And then the network, the reaction network, also will be composed of millions of nodes. But in terms of creating a reaction network, we use Network X, a library from, I don't know if you're familiar with that, and this is very efficient and no problem creating the network. Creating the network, let's say the bottleneck is the other steps, the previous steps. Creating the network itself, that step, the one that goes before the kinetics, this is fast. This is fast.
And the quality of the data from the network, from the aleatory composing all the nodes in complex systems, not complex as complex, just with many atoms or different kind of atoms, the quality of the output becomes worse with with more atoms, becomes, how can I say that?
I don't know, what do you mean by quality?
That maybe in the edge, when you're building aleatory edge nodes, some of the molecules that are real are fake or are difficult to be built, or
the molecules are built before that step. So you have all the optimized geometries, nodes in this case, or edges in the case of transition states. So if you trust your ab initio method or DFT method, then the reaction network is going to be based on that. And quality is going to be purely the quality of your ab initio DFT calculation. I don't know if we are on the same page.
Maybe I'll ask you later when you. Okay. Yeah, thanks.
So it was here, I guess. Yeah. So another way we do, and this is another thing we do to improve the efficiency of the method, is we sample for multiple minima. What do I mean by that? So this is in either way, MD simulations or chemical knowledge. We do these things. So obviously at the beginning beginning, we only have one minimum that we call here min 0, and everything starts from there. So we launch all trajectories from there, and they will find other structures, minima and transition states. This is in the first iteration, at the very beginning. Okay? But once you finish the first iteration, we do a second iteration. This I haven't mentioned before, but we do several iterations of the procedure. And why is that? Because in the second iteration, we obviously now have a bunch of different minima, like this one here, for instance. And you don't need to start from there. You can start from minimum 1, 2, 3, and 6. What do I gain with that? What is the advantage? Okay, the advantage is that you are going to sample everything in a more efficient way, because it is not the same starting from here and finding all the structures nearby than starting from here, there, and there, and there. I mean, it is more and more efficient, right? So this is what we do. We do everything in an iterative way. And obviously, you want to find something like this. This is number of transition states, number of trajectories. You want to get convergence at some point. You don't want to run these things, I don't know, maybe 1,000 times. Yeah, I typically use something like 10, 20 iterations, and with that, I'm happy. And if you find, the thing is, if you find the reactions of your interest in this 10 or 20 iterations, you can stop there. Right? You don't need to run 50, 100 iterations or something like that. And again, this is to be more efficient. This is, I guess this is understandable. I mean, we start from different minima, and this is better than starting from a single minimum. You go further away, you start from different minima. Okay? Because the trajectories are short. Remember that. Trajectories are very short. Okay, now this is an important point. So how do we analyze the snapshots that come out of the trajectories? Okay, suppose we have again, we have to use the adjacency matrix that I mentioned before. So suppose we have a simple reaction like this one here, in which this is an atom shift between, this is atom 1 that shifts between 2 and 5, right? So this is a simple reaction. And this is the reactant, this is the product, this is the adjacency for this reactant, this is the one for the product. They are obviously different because there is a bond that is broken, this one here, and a bond that is formed, this one here. So the thing is, what we do is basically we monitor this matrix along the trajectories, and we try to spot a change in one of the elements of the matrix, right? But the point is exactly how to pinpoint the exact location of the transition state. And for that, we use this inequality here that basically says that the maximum distance between this J runs for all atoms of the system. But now I'm focusing on this reaction here. So let's call J equals 1. So when the maximum distance between J and K, the K's are the neighbors of J. And there is one neighbor here only, which is atom 2. When this distance, when the maximum distance between J and K becomes greater than the minimum distance between J and L's, the L's are the atoms that are non-neighbors, non-bonded. Okay, and this will happen at some point in between this structure and that structure. And this is the simple definition we employ to pinpoint the exact location of the transition state. So we know the exact location, the time at which this transition occurs, and we also know which are the atoms involved in the process. So in this particular case are these 3 atoms, 1, 2, and 5. They are the 3 involved in the reaction. Okay? So the second step is very important. So once we know the atoms involved, this is a simple example for this molecule here. This is formic acid, and this is the reaction leading to CO plus water. This is a similar example because there is also now here there is 2 bond breakages. Yeah, 2 bond breakages and 1 bond formed here, I guess. Yes. The OH is formed and the CH and the OC are broken. So once we know that, what we do is, look, this is the highest point, and this is the point that we select. In this case, coincides with highest point along the energy profile. We freeze these 3 atoms and we relax the positions of the other 2. This is a very important step. And in this particular example, we are able to bring down the energy by about 100 joules per mole, which is a huge amount of energy. This is very important. This is like, I mean, you have the transition state, and then you have the normal modes, perpendicular normal modes, okay? And this is like going down here from in the perpendicular normal modes towards the transition state, towards the real transition state. So we relax the other atoms, the atoms that are not, that do not take part in the reaction, and we end up with a structure like this, which now is very close to the real transition state. Obviously, we still need to optimize it with eigenvector following. But look, this is 100 electrons per mole. So this is the geometry that comes out of the trajectories. We could use this geometry as well, but the energy is very high. So we need this step. We need to relax the atoms not involved in the reaction. So final step, as I said, is we take this geometry and we subject it to TS optimization using again the following.
What should we keep in mind when we make a matrix from a structural formula of the
Sorry, I can't hear you very well.
What should we keep in mind when we make in the matrices, adjacent matrices from the structure of the molecule? What is the basis of making a matrix?
What is the basis for making this matrix?
See.
Okay, you mean how do I know this is a 0, this is a 1?
Why we don't start it from 1, 0, 0, or why we follow the same pattern as you written here? This is my question.
Sorry, say it again.
My question is that why we follow the same pattern as you written here? Why we do not follow the same another pattern? Like why we do not start from 1, 0, 0, 0, 0, 1, 0, 0, like this?
I mean, this pattern here corresponds to this molecule. I mean, the diagonal is all zeros. It has to be like that. And then this one here, I don't know if I
wanted to know these things, why we choose such types of matrix who has only diagonal 0, but other element no. What is the philosophy behind that? Why we decided to do our analysis like this way? There is some interrelation between when we see some molecule, so we decide this type of methodology in order to fulfill our perspective of futuristic goals.
Porque existen las adjacent matrix en Go y otro tipo. ¿Cuál es la filosofía detrás de haber elegido las adjacent matrix?
So why adjacency matrix, you mean? Not other type of matrices?
No, this is the definition of adjacent matrix. I know because I am a mathematician. But why we follow this type of philosophy in order to fulfill this type of mathematics? When we see some molecule and we see their structure, and we found that this structure like this way at presented the slide. After that, we decide to analyze these things by computationally by using a mathematics. Then we choose half mathematics, and we decide why we select only adjacent matrix. Why do not select other unitary matrix, Hermione matrices, some other matrices?
Well, the thing is that I found this very, very useful for this case. This is, I mean, I'm not the only one to use this type of matrices.
No, I know many chemists uses this thing, but I wanted to know there is some philosophical point of view. I wanted to know the key point when the chemist or physicist decided to do their analysis or interpret their theory with the help of mathematics. Then what should they keep in mind in approaching this type of analysis?
What did they keep in mind?
What is the way of deciding this thing?
Well, the question is why do you choose this matrix type and not other?
No, I understand the question, but I don't know how to answer it. The thing is, you know, because this is simple. This is simple. It's a simple way just to.
There are many so simple.
But which ones? Which ones?
Why do not unitary matrices?
Sorry. I can.
Unitary matrices, diagonal matrices, many matrices is there. Why did
To
you
represent
decide
molecule,
to
to
that
represent
particular
molecule.
one? And how did you say that this is more simple for this type of thing?
Okay. This is. I would say this is simple. This is a simple way just to. This is also called connectivity matrix. This is a simple way to to know the connections of your molecule. To know how many bonds to have in your system. Which atoms are connected to which other atoms. This is a simple way to
if we decided like this, we started from 1 0 0 0 0, and if we started 0 1 0 0 0, and this is the follow the same representation formula, but this is not an adjacent matrix.
Yeah.
This is the another representation, and if we follow that, we do not get the same result as we describe here. So that's why I listen many authorities, many physicists, many mathematicians. They just started one thing and they just hidden this thing. I don't know what are the way they choose this thing. And after that, they just interpreted mathematics which comes out from the equations and all the things. And that as a researcher, I would like to know when some researcher or philosopher of mathematics, chemist, or physicist choose these things when they make a theory, then what should they keep in mind to interpret the theory according to their result or what they see from the observation?
I know.
Yeah, I just want to comment out. I mean, I'm not sure also whether I fully understand the problem, but basically, so if this is quite intuitive for chemists in the sense that you have both in the row and the column indicated each one of the atoms. So basically, each one of the vertices of that graph. So what you indicate with a 1 is intuitively a bond between two atoms. So it is basically the easiest way for chemists to understand this kind of problem. So this is the reason why we choose this and not.
I am not disagree with this. Why do you choose this?
But
This is not a matter. This is your task. You choose whatever you want. But instead of that, this is the same representation, and this is the same specific representation if we choose 0 1 0 0 0 and 0 1 1 1 1, and this is describe the same thing. And if we solve like this thing, we do not get a same result.
So I mean, this is whether a bond is broken or not. This is the whole point of the analysis, whether bonds can be broken. So if you have a 1, then it means that there exists a bond between two atoms. If you have a 0, then it means that you don't have a bond. So this is the real point of using this binary representation.
I have another, by the way, let me continue now, maybe. I will show you in a couple of slides one that I'm sure you will love, because it is there are other matrices, Laplacian, for instance. You know Laplacian?
Yeah.
Matrix? Laplacian? No. Well, I will show you the menu. Okay. Maybe you're happy with that. Okay, so again, this I have already mentioned. This is the last step. And then we have also another alternative. We don't need to use, by the way, we don't need to use matrices. We can use bond orders. This is more, chemical. And this we don't need matrices. Here there is no discussion. We just look at the bond orders. So here, look, we plot bond orders versus time. This plot here. And then we can also follow the derivative of the bond order. This is very useful because in this example, the reaction takes place at 3.1 picoseconds. Because look, this bond order goes from 1 to 0, and this one from 0 to 1, and so forth. So the reaction takes place here, 3.1 picoseconds. So it is very useful to plot the derivative as well, because the peaks in the derivative correspond to the reaction, to a sudden change in the bond orders. The only thing is that you have to distinguish between these peaks here corresponding to fluctuations in the bond order, but not a real reaction from these other ones. So you have to give a maximum and minimum value just to distinguish the different peaks. And this is some parameters that you need to do some fine tuning there of the parameters. But other than that, this method is very interesting. There is no matrices here involved. It's just the bond orders. And everything else is the same. So once you know the atoms, you relax the other atoms and so forth. Okay? But this is not based on geometry. It's based purely on the bond orders of the system. Okay, so these are the methods. These are the quantum engines which are interfaced to automaking. So we have MOPAC, Gaussian, and Entos Q-core. This one is free for academia, and this is for some empirical calculations and DFT as well. This is Gaussian, everybody knows. It's DFT, other type of high-level calculations, and MOPAC for semi-empirical calculations. Okay. We need these programs because we need single-ending methods. So we need to use the eigenvector following algorithm for the optimization of the structures. Okay? And this is not in mathematics. Okay, this is the slide I was talking about before. So this is again the adjacency matrix. This is the graph corresponding to this matrix, or vice versa. This is the matrix corresponding to this graph. And why do we use these things here? So here the reason is clear. Here the reason is because we want to compare structures, and also we want to know if the system, if we have an intact molecule, or if the system dissociated and we have fragments. Okay? So for the former, for the comparison of structures, we can use the eigenvalues of the adjacency matrix. So we calculate the eigenvalues, and these are invariant with respect to permutations of like atoms, and this is very interesting, running dynamic simulations. Or we use sprint coordinates. They are called sprint coordinates. This was published in PRL 2011. They can be constructed from the maximum eigenvalue and the corresponding eigenvector of the adjacency matrix. And again, they have the same properties of being invariant with respect to translations, rotations, and permutations of like atoms. This is interesting for NV simulations because there can be scrambling of atoms, hydrogen atoms, for instance. So we use the eigenvalues of these objects from, for the comparison. And then to distinguish fragments from intact molecules, we use the Laplacian. Laplacian is defined as the degree matrix. Degree is a diagonal matrix, and the degree is just the number of neighbors of each node. So here we have 2's because this is the corresponding Laplacian for this graph here. So we have 2 neighbors for each node. So we have 2's in the diagonal, and then so this is the degree minus the adjacency matrix. Well, this is the matrix. This is what it looks like. But the interesting thing comes with the eigenvalues, because the number of zeros here corresponds to the number of fragments. Here we have only one fragment, one molecule, 1 0. If we had 2 fragments, if the system already fragmented, then we have 2 zeros here, and so forth. If we have 3 fragments, 3 zeros. And this is the reason for using the Laplacian. Okay? So we use the adjacency, but also the Laplacian for these other properties. Okay. So these are the kind of things that we use to compare structures and to screen structures. And now I'm gonna move on to talk about the kinetics module of the. I didn't know the background of the audience, so I put here some slides. Maybe I can skip some of them. I don't know. This is chemical kinetics. I don't know how many of you are familiar with chemical kinetics. Only one. But I can talk a little bit. Chemical kinetics. So, for instance, if we want to study homogeneous catalysis, for instance, well, this is the typical way in which we write a given chemical reaction, where the small letters A, B, E, and F, they are the stoichiometric coefficients, and then capital A, B, E, and F are just the chemical species. This you know very well. We define the rate of reaction in this way, in which nu or y, the nu's are the stoichiometric coefficients, and this is the concentration of the species. This is also due to a course of chemical kinetics. This is very simple. So the coefficients are positive for products and negative for reactants. This is just an example for this reaction, N2 plus hydrogen leading to ammonia. This is the rate of reaction that can be expressed as a function of the variation of the concentration of nitrogen, hydrogen, or ammonia. And then the units depend on in which context we are talking about. I mean, in chemical kinetics, this is macroscopic thing, so we typically use molar concentration, and in chemical kinetics, we use molecules instead of moles. Okay? And so there is the rate law, and with photomaking, we can also predict rate laws, and this is interesting sometimes. I mean, the rate law is basically the relationship between the rate of reaction and the concentration of the species, something like this. So this would be the rate law. K is the rate constant that depends on temperature or pressure, temperature and pressure, sorry. But it could depend also on energy, depending on the type of system you want to simulate. I mean, if it is a thermal reaction, the depends on temperature. If it is a microcanonical reaction, fixed energy depends on the energy. And this is the rate coefficient. And then we have the concentrations of the species, and then the alphas, beta, and so forth. They are called the orders with respect of a given species. And the sum of the orders is the overall. This is just an example for several reactions. This is the rate of reaction for this one here, the composition of N2O5. This is another one for this other reaction. And this is a more complex rate law. This happens in many cases. I mean, you have rate laws like this, which are very complex, with the concentrations in the numerator and denominator as well. And towards the end of this lecture, I will show you an example of this complex rate law. And in general, the rate laws can be obtained experimentally or also by simulations, as I will show you in some minutes. So there is also, obviously, you need the reaction mechanisms, which is something that automaking also predicts. And this is just, you know, the number of different elementary steps, elementary reactions or elementary steps also called. So if you have, for instance, a reaction like this, you write the reaction like this, but it doesn't mean that the reaction goes in one step. Okay? Some cases, this reaction, other reactions are split in different elementary steps, like here. This reaction is actually a three-step elementary reaction, so there is 3 steps here. And so every single elementary step can be unimolecular, can be bimolecular. This, I suppose this you know. So for instance, this is a unimolecular reaction. Bimolecular reaction can be this one or this other one, for instance. So you have different examples of different chemical reactions with different complexity. And then there is the differential rate equations. And these differential rate equations, which are these ones here, for instance, look, the same example as before, you can write the derivative of the concentration of N2O5. N2O5 appears in this reaction here, and also in the first one. So it disappears in the first reaction, so that's why we have a negative sign here. And it appears also in the first one when you go from in the reverse direction, and then it disappears in the third reaction. Right? So you can write all the differential equations. The set of differential equations is also called the chemical master equation. Okay? I will mention chemical master equation afterwards, and it is exactly the same thing. You write all the equations, and you have to solve the equations. And solving the equations, you can get the rate law, you can get also the population or concentration of the species as a function of time, etc. Okay? So what we want to solve, what we want to do is to work out these equations. And there are different ways to solve the equations. One way is to diagonalize the matrix with the rate coefficients. There is also some analytical methods, or the one implemented in our program is called Kinetic Monte Carlo. It's a stochastic procedure, very simple one. People typically use it in gas surface reactions, Kinetic Monte Carlo, but you can also use it in gas phase, homogeneous catalysis. Basically, what we want is to solve these equations, to get the population or concentration of the species. So this, I am sure this you're familiar with. So not all points, I mean, if you run, I mean, this is a course on molecular dynamics. So molecular dynamics, all points are important because to propagate trajectories, and you need the gradient and the energy at all steps along the trajectory. So you can go, you can visit a minimum, you can visit a transition state, but between the minimum and the transition state, there is obviously many steps, and all steps are important because you want to integrate the trajectories and you want to have a good energy conservation. So you need to know all points along the test. But if you use the procedure I'm trying to explain today, not all points are important. The most important ones are actually the stationary points, the ones that I plot in the energy diagram. The minima and the transition states are the important ones. Because assuming that the process is statistical, assuming you can use some statistical theories for the rate coefficients, you can give the kinetics using statistical theories and just using information from the stationary points. You don't need all information for all points in the past. You only need potential energy searches. You only need information on the stationary points, those with gradient 0, which are the minima and the transition states. With that information is enough, assuming the statistical conditions are fulfilled. And we'll talk about that in a minute. So the important points for us are the minima, or the QDB geometries, which could be global minimum of the system. This is the lowest energy, potential energy of the past. Could be local minima. Local minima could be also called reaction intermediates in the language of chemists. And also conformers. Conformers are just minima, which are interconverted by rotations of points. There is no bond breakage whatsoever. And then the saddle points. Saddle points, well, the way to distinguish it, by the way, from a practical point of view, in the calculations, the way to distinguish minima from the transition states is to look at the vibrational frequency. You have to calculate the Hessian. The Hessian is the second derivative matrix. If you diagonalize the matrix and you get the eigenvalues of the matrix, they have to be all positive. Minima, they all have positive eigenvalues, therefore real frequencies. And then saddle points correspond to situations where you have more than one one or more than one negative eigenvalue corresponding to one imaginary vibrational frequency or more than one imaginary vibrational frequency. So you have different saddle points. First order saddles are those with only one negative eigenvalue, therefore one imaginary frequency, vibrational frequency. And they are the interesting ones in statistical theories like transition state theory or RRKM theory, for instance. They are the important ones for those theories, but there could be also second order saddles or third order saddles and so forth. They are interesting from a dynamics point of view, but not from a statistical point of view. Right? And actually, transition state is a first order saddle, and this is relevant for the study of chemical reactions, as I said. I mean, the name transition state is not exactly first order saddle because this name comes from this. This name is a name that has to do with the dynamics of the system. First order saddle is more a topological thing. So you have to have a barrier. This is a first order saddle. Transition state, you don't need to actually have a barrier. I mean, if you have a barrierless reaction without any barrier, still there is a transition state. Okay, so this is a dynamical concept. But anyway, people associate transition states with first order saddles, which is more or less okay, but there is also something which is called variational transition state theory, in which you have to locate the transition state at the right position, and it doesn't need to be exactly at the highest spot, at the barrier. It could be slightly off the barrier. Or even if you have a barrier reaction, as I said, there is a transition state, even though there is no barrier. So this is a dynamical concept. I don't know how long do I have still? I mean, how much time do I have?
You were talking for 55 minutes.
55 minutes. I've been speaking for 55 minutes. Yeah. Maybe we can stop now for 5 minutes and then continue. Yeah.
Intermediate mean is the
You have one negative frequency is what is the value of this?
Tendría que haber tomado 10. Tiene el cerebro plano.
I've got a very tight criteria to optimize the model, and then you will have all frequencies possible. With VAS, I know there are some issues, but there are some issues. And this is the maybe you are here, you're not why this is why you get this. Because when I realized this minimum returns to the other. It is probably an intermediate. Probably, as I said, if it is possible to change the algorithm and try something more tighter, alternative to you said there are several alternatives. There is Rowling string method, one called Rowling string, but this is not implemented in many programs. It's not in fast. Rowling string is an alternative. I'm not familiar with it. I know the name. But if there is a problem with the algorithm, I guess the problem is with the because 45 centimeters to my size, it means probably that if you have used something more stop when the gradient is 10 to the minus 3, maybe you're telling the problem. And if you say stop when the gradient is 10 to the minus 6, maybe you get it. Because the gradient is small.
Ya, bueno,
you are
problemas eso del pollo. Ahora se me está parando como sí. Empuro un poco la molécula, el criterio.
Change let's say the gradient. There are something more, something like 20 minus 6, 20 minus 9. Try that. See.
Ibas a preguntar a tu ver si coincidimos sobre matrices, pero la segunda parte o la primera.
Bueno, básicamente, le veo.
Small barrier, and then they just go deep.
Cuando me refería a calidad de datos, empiezan a formar matrices moleculares imposibles.
Bueno, primero
Y aún con los criterios que tienen.
Because it is very
Yo no entendía, por ejemplo, no tiene vale, pero si por ejemplo tenemos así, justo en el momento de reactividad, claro. Entonces, hola, tenemos preguntas. En plan, eso en verdad lo de la materia de ciencia, o sea, al principio, pero no lo te vamos a gritar. O sea, yo por ejemplo tengo la duda de, o sea, lo usan para evitar la LMD, ¿no?
También usamos como pero también lo puedes usar para evitar el MD.
Vale, y en el caso de que lo uses para evitar el MD, empiezas a componer unidades muy puras del fuego, de una forma...
En ese caso lo que hacemos es, tienes la matriz, cambias los elementos y pero ahí no sería lo primero que mínimo no es algo. En ese caso lo tienes a través del porque ahí lo modificas de acuerdo a las reglas de las valencias máximas y mínimas de cada átomo. Es un poco difícil. Este elemento no cambia de 1 a 0. ¿Va en contra de las reglas? Sí. Bueno. ¿Va a arriba, sí. Llevas un número. Entonces, ahora, pues conectas con el ND, y eso ya va todo automatizado. Sí. No, con el
pero el comando de SSH
bien, esa pregunta eso tiene que ver con esto. Sí, bueno, sí que sabes, sí que puedes. Puedes hacerlo.
O sea, mientras no haya una rotura del...
No, pero sí. Yo lo mencioné porque son demasiadas cosas. Las matrices normalmente son números enteros. Hay una normal, pero se pueden usar los elementos asociativos, son números reales. Esto va entre 0 y 1. 0,999. Ya tenemos información de esto. Y ahí distingue. Y ahí hace los autovalores de esto. Y el programa usa la flota. Usa esto. Estamos ahí pues tenemos fórmulas para explicar los autovalores. Pero estos elementos estos elementos están sacados de la línea de comunicación. Claro, el mismo artículo de los coordenadas sacan un vale 6 y 2. Esto va entre 0 y 1. Es un número real. La que más usamos sí. Sí, pero bueno, puedes hacer una simetría. Puedes hacerlo de screening y ahí en la fila. Si tienes un plano de simetría,
que cuando yo preguntaba por la calidad, me refería
yo no te entendía ahí eso de la calidad.
Me refería a que después del output que te sale, o sea, si cuando necesitas preguntas o por ejemplo con un antiómero, tienes una depuración mayor, si cuesta más tiempo de cálculo o no, si hay un límite en esto.
Porque la cinética los antiómeros así. Equivalente se identifica con Okay, so we were talking about the important points in the test, right? Which are basically the stationary points, right? So once we have those points fully optimized, we can carry on with the kinetics, right? So the aim here is to get rate coefficients, because knowing the rates, you can solve the chemical mass equation, right? The differential chemical equations. So you can. So, for instance, you might be interested in the case of T, thermal rates. Right? They typically depend like this on the inverse of the temperature. So this is the high temperature regime, which is typically very well characterized by a Reminius behavior. Then you have an intermediate regime, which there might be some tunneling, and then a low temperature regime, right? This is the quantum regime. There are several theories that work quite well for some of these regions. There is also, for unimolecular reactions, there is also the temperature, the dependence on the pressure as well. Although this has not been implemented in automaking so far, we plan to do it in the future. And so, as I said, so basically, for instance, if we want to simulate something at a given temperature, we can use transition state theory. This is the simplest formula for transition state theory. So, I am sure you're probably familiar with this formula. So this is the reaction path degeneracy. So again, we've been discussing of enantiomers and things like that. If a transition state has an optical isomer, for instance, then the minimum has no enantiomers, then there is the reaction path degeneracy is 2, because you have 2 exactly equivalent ways to go from reactor to products. So this is the reaction path degeneracy. Then there is Boltzmann constant, Planck's constant, and gas constant there. And then you have the temperature, and this is delta G of activation, the Gibbs energy of activation. This is the simplest formula. And you can, what we do is we use the rigid rotor harmonic oscillator formula to get delta G and nothing else. As I will be telling you towards the end of the lecture, the plan is now to replace this module with something better. So there is people in our group in which they work on tunneling effects, variational effects, and things like that. And harmonicity, which is not included here. So the idea is to use better theories for the rate coefficients. But so far, we have this simple formula for the case of T, or if you're interested in microcanonical situation, microcanonical conditions, then you can use RRKN theory. This is the sum of states, the transition state. This is again Planck's constant, and this is the density of states of the reactor. You can use this one or the other one depending on your interest. These are the assumptions of the statistical theories. So these are statistical theories, and the way and the reason why they are called statistical is because basically they have a number of assumptions, which are shown here. Basically, we assume a Boltzmann distribution for transition fast energy redistribution in the case of RRKM theory compared to the rate of reaction. The transition state is not recrossed, meaning that once we get to the dividing surface, once we get there, we proceed to the products. We don't go back to the reactions. This is the no recrossing assumption. And the reaction follows the IRC, so we are going to follow the IRC. And this is not true in some cases. I mean, there is, I'm sure you have heard of bifurcations of the reaction path, for instance. This happens in organic chemistry many times. And I mean, the IRC leads you from one place to another, but if there is a bifurcation, you can end up in one product or the other, whereas the IRC will lead you only to one of these situations. So the only way to solve that is to run dynamics. There is no other way. You cannot use statistical theories if you have a bifurcation of the path, of the minimum energy path. And then another assumption, at least in this formalism, is that the nuclei behave according to classical mechanics. There is no tunneling effect. But as I said, there are simple ways to solve that problem, which is just with a factor here. We put here a factor that contains the contribution of tunneling. That's a way to include tunneling in the calculation. And yeah. So once you have the rate coefficients, either thermal or microcanonical, this is again the same equations I mentioned before. This is the chemical master equation, but this is in a more compact form. This N or C, N is for population, C is for concentration. This is an array with the populations of the species as a function of time, and then the M are the equations with the rate coefficients. Positive, if positive is if a particular species is forming, or negative if a particular species is disappearing, etc. So you have this equation and you can solve it. And the way we solve it here is with KMC, kinetic metacount. So this is a stochastic procedure in which basically you just need to draw two random numbers. First one is to know how much time we spend at the given minimum. We use this simple formula to know how much we stay there. And then we need a second random number, R2, to decide whether from I we go from I to J or from I to L. Here is more probable to go from I to J. Look at the boxes size here, for instance, because there is a lower barrier there. So it is a very simple way to solve the kinetics. Right? And you propagate that for many steps until the reactants completely disappear, and all you have now is just the products. So this is the way we implemented the solution of the chemical master equation in our program. This is the last release. It appeared in JCC last year, and this is the wiki of the program. Today we will have the chance to check what is there. I mean, you can download the program there. There is also some other information. There is a tutorial, and there is also a list of different applications there. This is a very useful tool that we have published in February of this year in collaboration with these people, Carlos Bo, Diego Garay, and Moises Alvarez from Tarragona, ICIQ of Tarragona. And what they have done is they have created this. I mean, this is just a static picture, but probably this afternoon I will have a chance to show you the interactive one. So this is an interactive HTML in which you can see again another graph. This is another graph, but we use graphs here at two levels. First one I have already mentioned. So we say a graph is a molecule, but here a graph is a different thing. A graph here represents all the pathways in the system. So here a node is basically a minimum energy structure. Could be a minimum, could be a product, whatever. And then an edge in the graph is a transition state, a pathway. So you can represent the reaction network in a graph like this. Okay, and this will be the graph of your system. And then, since this is interactive, and I will show you, well, I don't know, 6:30 or whatever. I will show you how to do it. You can hover over the nodes to get information, for instance, on the energy, the chemical formula, the label, and then if you click on a node, you can visualize the geometry of the node, you can even visualize the normal modes, etc. You can plot the energy diagram. Sometimes this is very dense, I mean, you have many structures, but there is the possibility to filter. To filter, you know, the number of nodes in the system and the number of steps you plot here by telling, give me the path that connecting this minimum with this other one through a maximum of 4 steps, or through a maximum of only 2 elementary steps, for instance. That way you get rid of many pathways, or you can also filter by energy. You can cut out everything above, I don't know, maybe 80 kilograms per mole, or you can filter by the species involved. For instance, just tell me which pathways contain minimum 3, for instance. So you can do all these things interactively. Okay. And also there is the command line possibility, which allows you to do everything from the command line in both ways. I will show you this afternoon, as I say. Okay, everything that I said so far is to get saddle points, right? So we want to get barriers. But there are many important reactions that go without a barrier. There is no barrier reaction. And recently, also in the same publication, ACS Physical Chemistry Go, we came up with a simple algorithm to identify barrier reactions. I mean, identify those reactions from a mechanistic point of view. I mean, just drawing the reaction is not very complicated, so I will tell you in a minute. The problem is if you want to simulate the kinetics. This I can tell you more details in the afternoon, but for instance, for organometallic catalysis, it's a little bit more simpler. But in gas phase, it's more complicated because in gas phase, studying the dissociation of a barrierless process is very complex. Because as I said before, you have to place the location of the transition state variation. Okay? You need to know, and the way you do it is just to you try to minimize the recrossings of the transition state. Okay? And this is not so straightforward. But from a mechanistic point of view, identifying barrier reactions is very easy. So from the minima, what we do is we calculate the bond orders and we identify bonds with bond orders lower than a given threshold, like 1.5, for instance. Then we break those bonds using external forces. Once we break the bonds, we have a path there, and then we compare this path with the paths that we have already computed with a barrier. If there is no match between both sets of paths, then we are sure we have a path without a barrier. But just to make it more sure that the path has no barrier, we can also run NEB to confirm there is no barrier there. So this is very simple to obtain. As I said, different story is to obtain the kinetics in a fully automated fashion. You can do it manually, of course, but automatically it's not so simple. It's not so straightforward. Okay, now, yeah.
When you run the NEV to confirm that there is a barrierless reaction, I mean the NEV algorithm will find the TS, no? Even though there is not a barrier, as you said before, if you have no barrier, there is also a transition state.
Yeah, but the NEV again is what it finds is geometries, so it's topology. And as I said, transition state is a dynamical concept. So NEV is going to give you a set of geometries along the path, and you can plot it, and you can see if there is a barrier or there is no barrier. That's it. NEV is not going to provide you the transition state. Transition state you can get the transition state using variational transition state theory, for instance, but there is many complications, like for instance, there is the transitional modes with very low frequencies, for instance, that are not actually vibrational modes. They are more like rotations, hidden rotations and stuff like that. So the way you treat those low frequency vibrations is crucial. So some people, basically what they do is they solve the phase integral, things like that. So it's not simple. It's not simple. But to get a transition state, you need a dynamical theory. You need a statistical theory, like transition state theory. There is also flexible transition state theory by Wittgenstein. So there are ways to do that, but not with NEV. NEV gives you geometries along the path. And obviously, you can check if there is a barrier or not, a saddle point, to be precise. But to locate the transition state, you need something else. So now we move on to applications. Again, this is the list of different problems we have tackled so far. Not only we and also other research groups. We studied some of these systems, and other people in other groups studied also some of these systems. And today, well, I had selected these systems 4, 5, 6, but I don't know if we are going to have time to speak about all of them. Maybe if you have a preference, you can tell me, or I don't know. I just going to start, and then we don't need to talk about all of them, of course. So because just to repeat the same story is not. I mean, just this is the same system I showed at the beginning. This is vinyl cyanide, the one with 7 atoms. And here I'm showing only the pathways leading to hydrogen cyanide. Okay? Well, the reason for studying hydrogen cyanide elimination pathways is because obviously there is typically experiments which we want to simulate, but here there is an experiment in which they look at the branching ratios between the co-products of hydrogen cyanide. The possible co-products are vinylidene and acetylene, which are these two here, in blue and red. So we try to do that, well, in blue and red in this case. There is also another vinylidene there in green. So these are the possible co-products of HCl. And this is the branching ratio obtained in experiments. So we did the calculations with, so first by hand, and we found, as I said at the beginning, the blue, the red, and the black pathways. And then some time later, I forgot, maybe, because this was in 2015, maybe some months later, with automaking, we studied the same system, and we found also the green one. And this is interesting because this one turned out to be very competitive. This is from the yields, as a function of energy. So here, this is a microcanonical study because this is, they used a laser, 193 nanometers. So this goes to the excited state, but then there is internal conversion into the ground state. And the HCl elimination takes place in the ground electronic state. And this is what we study. So this is a function of energy. And the laser is 193 nanometers, which is about 150 kHz approximately. So it's like here. So the green pathway is still important, right? So the green pathway that was missed in the first calculations was an important one. And when we put everything in the simulator, in the kinetic simulator, this is what we get. Right? We are not far from the experiments. This is another example. We studied the photolysis of propanol. We obviously studied the pathways, but here I'm just showing the minimum energy structures. Right? Just to see the comparison between using chemical intuition with using something, an automated program. Right? So this is propanol, which is the lowest energy structure in the same chemical formula. And there is a previous study by a research group. The paper was published in 2011. They used this level of theory. They have 1, 2, 3, 4, 5 structures shown here. Okay? They found these 5 structures. So with these circles. But then 4 years later, with automaking, we found all the other ones, 32 structures. Okay? And this does not include the sampling of the conformational space. Okay? If you include the conformers, you get something like 70 structures. Okay? So I guess if I look at some of them, like minimum 3 and then 5, 6, 7, etc., they are low energy structures. They are depending on the experiments that they could be important. Okay, this is another study. I mean, there are so many studies that this looks like, I don't want to overwhelm you with too many applications. Again, stop me anytime if you have questions, something. And this is I guess this was a very interesting collaboration with people from Temple, Philadelphia. They did experiments, and what they do, this is the group of Highland guys in Temple, Philadelphia. And what they do is they do the photolysis of this molecule. I will tell you the reason in a minute. But what they do is that they do the photolysis of this molecule. Again, most of the chemistry happens in the excited state, and then there is a cascading internal conversion process leading to the ground state, ground electronic state. And then what they do is they use time-resolved infrared emission spectra to probe the different products. And they found 2 peaks here, 2 bands here, which are consistent with both isomers, hydrogen cyanide and hydrogen isocyanide molecules. And the ratio they get is approximately 0.1. The reason for studying this is because in the interstellar medium, that's why this was published in APJ, the physical journal. The reason of these two isomers, HNC, HCN, is way bigger than the one expected on account of their energies. I mean, if you get the branching ratio of these two molecules at 100 Kelvin, which is approximately the temperature of the ISN, you get 10 to the minus 33, because this one is approximately 40 gigacalories per mole, more stable than the other one. So you get 10 to the minus 33 at 100 Kelvin versus 10 to the minus 1 in the experiments. And also in the interstellar medium, there is an overabundance of this molecule, and the ratio is also like that. HNC over HCN is approximately 0.1. So the reason for this study was to try to speculate that the photolysis of this molecule, because there is also a lot of radiation in the interstellar medium, could explain somehow the overabundance of this isomer. Right? Obviously, this cannot be the only reason. There might be other molecules containing the cyano group, etc. But this is just an example of typical explanation of why there could be this overabundance. So after this interesting result, they came to us to see whether we could study the mechanism leading to hydrogen cyanide in the ground state. And this is what we found. We found that these two transition states that lead to the two isomers, hydrogen cyanide and hydrogen isocyanide, they are triple dissociations, as you can see. So you form three fragments, three molecules, but you form HNC and HCN. Okay, and interestingly, we found exactly the same, not exactly, but close to the experimental ratio, so close to 0.1, and also close to the one in the ISN. And in the experiments, they are capable of measuring indirectly, but measuring the vibrational energy content of the two molecules. This is the black lines. The black lines is the vibrational energy of both species. So we propagated the trajectories in the ground state. This was a different trajectory calculation from the transition states towards the products, and we calculated the energies. The energies are these blue lines here. And look at the comparison. The comparison is also very good with experimental. So we were very happy with this collaboration as well. Okay, this is another system. We studied this system for one reason. I mean, this is the also analysis of alpha binding. The reason for studying this was to compare the performance of both standard MD and DXD that I mentioned at the beginning. So there is standard MD, you just put a lot of energy, and with boxed MD, what you do is you use different boxes of energy, and you can find the dynamics in one box, and you sample one box and see what happens there. And then you go to the next one, and so on. So this is this graph here shows the graph with the standard MD results, and this graph here shows the network with the DXD results. Both of them for the same simulation time, not computational time. As I said, that there is an issue with this calculation. For the same simulation time, which I forgot how much it was. I guess 1 nanosecond in total. For the total simulation time, look, so this we get more density of edges here, more nodes here for DXD compared to standard MD, which again is telling us that this is more efficient than DXD. Although again there is this issue, this computational issue of this latency problem. This is related to the way the calculations need to get the gradients, which is through this ASE library. But this is another thing. This is another story. And here you see also some, for the chemists, this is something better to look at the structures. And so you see the different mechanisms. In blue, you see what you get with standard MD and DXD, with both of them in blue. But in red, you see some mechanisms that you only find with DXD. So somebody can tell me, okay, so if DXD is much better, Why you still use standard MD? Well, I have to tell. Again, this is comparing the same simulation time. Obviously, this is just one iteration of the process that I mentioned at the beginning. If you run the thing for 5, 10 iterations, you end up getting exactly the same number of pathways and so on. But you want to be efficient. This is just a comparison for the same simulation time. For the same simulation time. This is why we still use standard MD. I mean, we use brute force and let's say 20, 30 iterations, and then we go to path. So, Juanjo, tell me so we have until 2:15 or something.
Yeah, in theory, you can, as we start late, maybe 2:15.
I think I'm going to finish before that because we don't need again. I mean, well, this I don't. Let me just show you this. I don't want to expect you to see anything here. Actually, the reviewer of this paper was very funny. He was like, I think this graph, I don't see anything. Either make it bigger or just remove it from the publication. And this is just to show the complexity of kind of things you can find. I mean, here we found thousands of nodes, and this is indole. Okay, and we studied the decomposition of the molecule. You get thousands of nodes. And this is 2 levels of theory. This is semi-empirical calculation. This is ab initio or DFT, I forgot. And this is the radical. There is also a radical when you remove hydrogen, you get a radical, and this is the node is simpler for the radical. There are fewer reactions, still complex. Right? Okay, and from this, using this tool, I mentioned these AMK tools, the interactive tool, you are able to plot these things automatically without having to. I mean, this is very interesting to navigate through this complexity here. So you tell the program, okay, tell me all the pathways leading to hydrogen cyanide, and then you can get this beautiful plots. I mean, without the molecules, of course. I mean, this I did by hand. You get you get the energy profiles, and you have to embed the molecules in the plot by hand. But I mean, why hydrogen cyanide? This is not. I mean, this is not my favorite molecule. The only reason is again here there is a study of the pyrolysis of the molecule, and in a previous study they focused on these pathways also. And these are new. All of them are new. So these pathways are completely new. So they found all the pathways, but not these ones. So it was found thanks to. And also there is some implications in astrochemistry, because we propose also a pathway that we found for the formation of indole. Indole is here, right here, and from these 2 reactants, from methylene and phenyl isocyanide molecules. Both of them found in the interstellar medium, so they are here. They are PR155. They are here, and the thing is that this reaction goes without a barrier. I mean, there are barriers here, but I mean a barrier with respect to reactants. And this means that this is a feasible reaction in the ISN. The reason is that there is, I mean, the gas density up there is very low. And that means that the energy, I mean, the molecules are not sterilized by collision. So you cannot go, you don't go to the bottom of the well. Because if you go there, you stay there forever. The energy of the system is going to be like that. So this is a feasible pathway. I mean, another story is what is the rate for that. We don't know. I mean, we haven't completed the rate, but this is a feasible pathway in the gas phase, because many of these reactions take place in ices or in dust grains or something like that, but this is in gas phase. So this is a possible mechanism for the formation of indole in the interstellar medium. And this is another example. I think I'm going to skip this one. This is, I mean, there's also the possibility to study van der Waals interactions. And this is interesting because this is simple, but the way to study this is just to expand the definition of the because this is another again, this is adjacency matrix, but this is has been expanded. So this is in a block. You have different blocks here. One for F. So you have 2 fragments, F and G, and you have a adjacency matrix for F, another one for G, and then another one for the interaction. And the way to define the matrices, these ones here depend on the covariant radii to define the 1s and the 0s. And for FG, you look at the van der Waals radii, define the ones and the zeros. And that way you proceed exactly the same way, and you can get covalent structures, covalently bonded structures, as well as van der Waals structures. So this is an example for this system, NO2 piling system. These are the most stable structures shown here. Okay, these are the connections. We obviously get also the transition states, and this is something that we can do. I guess there is an example this afternoon. We'll probably have the chance to look at one of these examples. Okay? And what are we doing now? We are trying to expand the capabilities and the different applications we can study with automaking. This is something we are doing with Nestor Aguirre. Nestor did the PhD here. Maybe some of you know him. And he's now in Amsterdam. And he's got this program, N3C, with which you can simulate dissociative photoionization processes, like this one here. You take methanol, you photoionize the molecule, and you get this breakdown diagram. This is the name of the diagram. So you basically have the decay of methanol, and then the formation of different products. It's a function of photon energy. So this is the experimental one, and this is the simulated one with N3C. N3C is based basically on the density of states of the different fragments. Okay, so you calculate the density of states of this fragment here, this other fragment, and the probability of getting a fragment is proportional to the number of density of the states at a given energy. This is fine, and you get qualitatively good agreement with the experiment. But the thing is, for some reactions there is a barrier. There are barriers. And this is a bottleneck, and this can change the plot, the diagram. And this is what we are trying to do. So we are trying to improve on that. And look, this is the combination of N3C with the inclusion of transition states. We are improving, at least this one. This curve is more similar than the experimental one. The other ones are also probably pretty similar. We haven't finished yet. The calculations are still, these are some preliminary results, but we are working on that right now. And also, as I said, we are trying to improve the kinetics module. So Antonio and David, they are my colleagues at the University of Santiago. They are responsible. They developed Torsiflex for sampling conformational flexibility of molecules, and Pilgrim. And Pilgrim is for accurate calculation of rate coefficients, including tunneling, including variational effects, including harmonicity, including multi-structural effects. Multi-structural meaning when you have different conformers that react, leading to also a bunch of different conformers in the products or transition states. You can include those effects in Pilgrim. And so what we are doing is this. So this would be the workflow in the future. You get the input geometry. Automaking would provide a reaction network. The reaction network could be in the future complemented with the conformers, and everything will be fed with Pilgrim to predict accurate kinetics. Okay? And then, last but not least, automaking would be possible without the help of many people. They all contributed one way or another, and also it was the supercomputer, the Galicia Supercomputer Center, and the funding bodies. Thank you very much for listening to me.
They have time for questions.
Yeah, sorry, I just only one question. Have you ever tried, I mean, first, if it is possible, and then if you have tried to apply this to study raw things, but kind of a cluster method that you only select the active site, very small residues, and just fits the atoms so the rest doesn't move, and apply this to these parts specifically?
So, have I tried? No, I haven't so far. Is it possible? I think it is. I think it is possible. Instead of using NP simulations, in that case, I would use chemical knowledge, which is probably more suited for that, more suitable for that. I would use something like this. You select the active atoms, and then you do all transformations within those active atoms. This is what I would do. Because MD simulations, you can fix the other atoms, as you said, but I guess this could be better, because still fixing the other atoms, here you can constrain even more your search, because you can just define, for instance, the valence of the atoms, and also the maximum and minimum number of bonds. If you have an idea of the type of reactions you want to study, maybe you can neglect, for instance, reactions that break 3 bonds and something like that. With MD, you get everything. You get really exotic transition state structures, maybe some of them with really very high energy, which could be fine for a didactic point of view. But if you want to study a protein, I would use something like this. I do define the active atoms and all these things, and try to restrict as much as possible the number of combinations. Because MD, I mean, still fixing many atoms, you know, even for indole is a small molecule, and you get thousands of nodes. For a protein, I don't know. And you have to compute. Then you can fix things, but then you have to optimize everything. There you have to optimize everything.
Because there is the cluster method that you take.
Okay, cluster method. Okay,
yeah, you only extract that part of the active side, and you forget about the rest of the protein. And this is quite fast. You're calculating femtoseconds.
Okay.
So the rest of the motion of the protein actually shouldn't be a big deal. So this is the approach that I was wondering if you can use this for.
I would say yes, and I will use this.
Okay.
For that case, I haven't tried. Okay. I mean, biggest system we tried is 120 atom system. Is C60 dimer. C60 dimer. There was a Portuguese guy. There was a Portuguese guy in my group 2 years ago. He was studying the dimers of C60. This is the biggest one. Yeah. Thanks. But this is not very common. This was just
More questions? Okay, if this is not the case, let's thank again Emilio. Okay, now we do a break for lunch. We have 1.5 hours, so we are back at 20 to 4, but not here, in the module number 6. So you have to go upstairs 1 floor, okay? The module number 6. 20 to 4. If you want to use your laptop for the computer exercises, it is okay.